Hey guys, so welcome to lesson 2 in our states of matter unit. Last time we learned a little bit about the kinetic theory of gases. Today we're going to get into how to do a little bit more math and convert between units of pressure and temperature. So important stuff today. So let's go ahead and get started. So after today, you should be able to convert in between units of pressure. Remember, we have 3 different units of pressure. We're going to go over that again today. And you're going to be able to explain what will happen mathematically to the average kinetic energy of particles if temperature changes. So let's recall that gas pressure is caused by these collisions that happen when gas particles bump into each other. Okay, so the simultaneous collisions of gas particles. And pressure can be measured in 3 different units. We have atmospheres, we have kilopascals, and we have millimeters of mercury. Good thing is, all pressure conversions can be done in one step. So if you're doing this, you're going to only have to multiply and divide once, or set up like one T or set of boxes. Okay, so that's going to be pretty easy for us to get going. So let's take a look at this example. We're already ready to go. So it says the pressure inside a balloon is 4.17 atmospheres. How many kilopascals is this? And in your notes and right here on the screen, we have 3 different conversion factors that we can use. We have 1 atmosphere, we have 760 millimeters of mercury, or we have 101.3 kilopascals. So let's take a look at how this problem is broken down. So the pressure inside a balloon is 4.17 atmospheres. How many kilopascals is this? We have our known and our unknown. Our known is 4.17 atmospheres. Our unknown is how many kilopascals. So what we're going to do is set up some boxes, or if you want to multiply like I have on the screen, that's just as fair. Remember, we're canceling units. What we want is on top. What we want to get rid of is on bottom. Okay, so we start off with our known 4.17 atmospheres. What we want is kilopascals, and the number for that in our notes is 101.3. What we want to get rid of, right, one on top, one on bottom, we can cancel those out. That's atmospheres. And in our notes it says we have 1 atmosphere. So once you multiply the top, divide by the bottom, you're going to get an answer. And remember, your known has 3 significant figures, so your answer should also have 3 significant figures, which is why I rounded to 422 kilopascals. So hopefully not too bad. We're just multiplying and dividing there, converting from atmospheres to kilopascals. So let's talk a little bit more about kinetic energy. So temperature is really a measure of the amount of kinetic energy a sample of matter has. But not all particles in the sample have the same amount of kinetic energy. Okay, most of them have an average amount of kinetic energy, but due to those collisions that are happening, some of them are going to get bounced off of and move a little bit faster, and some of them are going to collide and move a little bit slower. So it just depends, but most of those particles are moving with the average speed. Okay, and I want you to take a look at that graph in the top right corner. It's also in the bottom right corner of your notes. So let's take a look. Let's take a look at that blue curve. That is the cold gas. If you notice those cold gases, okay, that peak right there, that represents the average amount. So on average, those cold gases, they're scooted to the left, okay? So if you look on the bottom, it says the speed of molecules. They're scooted over to the left. They're not moving as fast when they're cold. Let's take a look at that red curve. That is a hot gas. So if we're increasing that temperature, more kinetic energy more speed. Okay, so hot gases move a lot faster than cold gases. Cold gases are nice and slow. So the average kinetic energy is actually directly proportional to the Kelvin temperature. So when we move the Kelvin temperature, it's going to directly affect the kinetic energy of our gas. So the formula to calculate temperature in Kelvin, and we've already done this before earlier in the year, but just as a refresher, Kelvin is degrees Celsius plus 273. And Kelvin can never be a negative number, so watch out for that. So the example here is the room temperature is 25 degrees Celsius. What is this in Kelvin? So all we're going to do is use that formula that we figured out, degrees Celsius plus 273. Go ahead and plug in your 25 degrees Celsius, and that is going to equal 298 Kelvin. And remember, Kelvin does not have a little degree symbol like Celsius and Fahrenheit, so just watch out for that. So as temperature decreases, particles move slower and slower, and we saw that when we looked at that blue curve, right? Temperature decrease, they're moving nice and slow. So the particles would theoretically stop when you get to 0 Kelvin, right? 0 temperature would mean 0 kinetic energy. But turns out this doesn't quite happen. Okay, one of those reasons is because of the kinetic theory. Even if those gases have stopped moving and colliding with each other, they're still vibrating in place. So not all movement stops. And another reason for this is because the temperature of 0 Kelvin has yet to be reached. It's a theoretic temperature, so nobody knows for sure what's going on at 0 Kelvin. It's so cold, nobody's been able to reach that level of coldness yet. So let's take a step back. Remember, we've used this before, but we have STP, which stands for standard temperature and pressure. And standard temperature and pressure, the temperature equals 0 degrees Celsius or 273 Kelvin. So that's our standard temperature that we're going to be using. Okay, let's take a look. We've talked about kinetic energy a little bit and how colder gases move slow, hotter gases move fast. Now let's take a look at our proportionalities. So let's look at this example. If temperature goes from 200 Kelvin to 400 Kelvin, then we're going to say, since it's direct, that it's going to double. Okay, and we know that we're going to put the final temperature over the initial. If we divide, that's a factor of 2. So the kinetic energy has doubled. Okay, so directly proportional, one more time. If we double that temperature, we're doubling that average kinetic energy. Okay, a couple more. Let's look at this top example. If temperature goes from 100 Kelvin to 300 Kelvin, right, we're upping it by a factor of 3. So this average kinetic energy is going to triple. Pretty easy one. Now this second example, let's do the reverse. What if we go from 300 Kelvin to 100 Kelvin and decrease that temperature? If we decrease the temperature by 3 factors, then the average kinetic energy will be a third of what it used to be. And let's take a look at that last one on your notes. But before we do, stop. Take a look at those notes. That last example shows temperature in Celsius. Remember, we can only do proportionalities in Kelvin, not in Celsius. It won't work. So what we're going to have to do first is, you guessed it, change Celsius to Kelvin. So If the temperature goes from negative 73 degrees Celsius to 127 degrees Celsius, what will the average kinetic energy be? We're going to have to add 273 to each of those numbers, get them up to standard, right? Get them up to STP. We're going to use it for Kelvin. Okay, so now we have 200 to 400. If we're going from 200 to 400, that's a factor of 2. We're going to double our kinetic energy. Awesome. So we are finished with this lesson. It was a quick and easy one, but the things I want you to take a special note of are converting between pressure units. We have 1 atmosphere, 760 millimeters of mercury, and 101.3 kilopascals. I want you to remember that temperature has a big effect on the speed and average kinetic energy of gas particles. So the colder the gas, the slower it's moving and the lower the kinetic energy. The hotter the gas, it's going to move faster and have more kinetic energy. And also just remember, if you were doing proportionality and you want to check temperature versus kinetic energy, you have to work in Kelvin. So if you were presented a problem in Celsius, go ahead and change to Kelvin and you'll be right on your way. So good lesson. If you need me, message me on Remind or on Microsoft Teams, and I'll see you in the next one.